Geoscience Connections leads you through a fascinating journey through the Earth's history. The timeline starts from the formation of our planet and across billions of years when humans became Earth's inhabitants. On the one hand, the intelligent human brain allowed for the development of technologies and a complex society. On the other hand, humans have participated in the uncontrolled exploitation of our natural resources and are thought to have caused many problems to other living beings on our planet. IUGG geoscientists help us to understand Earth processes, bring us hope for the problems humanity faces, and solutions to a more sustainable Earth.
So, gravity is a universal force that brings objects together and makes them act like an invisible magnet that attracts everything to itself. This force is fundamental to the creation and shaping of the celestial bodies, including the planets. In our early solar system, the dust collided and stuck together because of the gravity, gradually forming larger and larger bodies, and finally planets like the Earth. The Earth reached a point where it was large enough to have sufficient gravity to attract the meteorite that brought water to create the ocean. Even today, this force keeps everything on the Earth, including the atmosphere, the ocean, and ourselves. Gravity also drives the Earth's interaction with the Sun, and it creates the years and the seasons. Without it, everything would float in space, and gravity therefore played a vital role for mankind. After countless collisions, the early Earth transformed from a chaotic mess into a spherical shape. And it's because the gravity drags equally on all sides, and it constrains the matter in a three-dimensional circle, otherwise a sphere. While our planet is almost spherical, it's not a perfect sphere, but it's flattened on the pole and it's like a bulge on the equator. And it's like a balloon that spins, that deforms because of the centrifugal forces. In fact, the Earth is even more complex than this ellipsoidal shape. The non-regular distribution of mass caused by mountains, tectonic plates, and other geological features inside the Earth create irregularities in the Earth shape. This is the case, for example, with the Himalayas mountain that have a significant signature in the Earth shape. These anomalies are observable with the measurement of the gravity. Currently, this precise measurement is carried out using satellites that allow us to cover the entire Earth surface. And for example, with gravity field variation, this satellite can measure the exact level of the ocean with an accuracy of 1 centimeter. They provide great insight into the density and the exact composition of the Earth's interior and surface. We can even measure gravity field variation through time. It allows to study geology and climate, like big seismic events, continental hydrology, ocean and ice melting.
The geomagnetic field of Earth is incredibly important for all life, but also for modern technology that humans use every day. However, we cannot touch the magnetic field, and we can only see the effect of it, such as when iron filings align with a bar magnet, or the northern lights of the Earth's aurora. This invisible force attracts oppositely charged electrical particles together and spreads infinitely outwards from the source, getting weaker with distance. The main component of the Earth's magnetic field that we can feel on the surface is the movement of liquid iron in the Earth's outer core. So how does the Earth's magnetic field affect nature? Firstly, the Earth's magnetic field provides a powerful natural shield which protects life from particles and energy that is released from the sun during solar flares. Without this protection, life would be exposed to radiation which would damage the DNA that contains the genetic information. In fact, the aurora is produced when these solar particles interact with this protective shield at high latitudes. Animals have adapted to use the magnetic field to their advantage, and it is thought that animals such as whales, birds, and even bees use the magnetic field to navigate. Humans also use the magnetic field for navigation, and magnetic models are incorporated into government systems, underground drilling, satellite orientation, and a lot more. If you've got maps on your smartphone, then you'll be using a magnetometer when you go from A to B. Another important thing about the Earth's magnetic field is that it is one of the few tools that scientists can use to study the Earth's deep interior, especially in history. Some scientists use samples from lava flows or rocks with magnetic grains in them to look at how the magnetic field has changed over hundreds of thousands of years. This allows us to look into how the Earth formed, how the Earth's crust has changed, and how the magnetic field has changed in direction and in strength. Studying the Earth's history provides vital information for how the Earth is operating now and will operate in the future. If we want to predict magnetic field change for our technological systems, then we need to be able to model how the field has changed in the past on long and short timescales. The boundary between the Earth's core and the mantle is the biggest transition after the air meeting the Earth's crust that we live on. This boundary is between kilometers of molten rock, approximately the texture of sticky syrup, overlaying a liquid metal that is approximately as runny as water due to the extreme pressure and temperatures. On the core side, the cooling of the Earth from its formation powers turbulent flow and it forms the inner core. But the mantle is much thicker and moves much more slowly. The slow flow of the mantle is controlling the amount of heat that the core loses. Interestingly, the mantle is not the same everywhere, and we can use large shaking from earthquakes to see these differences. The largest scale heterogeneities are two blobs under the Pacific and Africa, which slow the earthquake waves that pass through them. Amazingly, there is a lot of debate over what these blobs are and how they formed, and what effect they will have on the core field. These blobs are called the large low-velocity provinces and potentially affect the magnetic field generated. We believe that these blobs are hot compared to the surrounding mantle, which would mean that there is less heat escaping from the core underneath these regions. One theory is that these hotter regions could slow core surface flow due to the smaller temperature difference between the core and the mantle. Alternatively, other interactions might be happening at the core-mantle boundary. Chemical reactions might be happening to form a layer of different composition, and it may be different under the large low-velocity provinces as opposed to outside. Another possibility is that there are variations in the height of this boundary, which would be like mountains on the Earth's surface, but deep inside the Earth. With so many uncertainties, we have to consider multiple sciences to investigate this boundary. The magnetic field will place additional constraints on the core mantle boundary, and hopefully ongoing research will allow us to understand the interaction between the core and the mantle in the future.
Where the crust breaks and whether the pieces of the crust breaks into bigger or smaller pieces depends on the heat inside the Earth. The crust pieces are what we call tectonic plates. The tectonic plates are our planet's outermost layer and float over a hot molten inner layer of the Earth. And guess what? There is a whole theory behind explaining the movement. But wait, did you know that the tectonic plates constantly move relative to one another? Well, it might not seem like that, but indeed they do. Some move faster than others, but on average, the tectonic plates move approximately at the rate at which fingernails grow. Plate tectonics is a theory that explains a wide range of geological structures. It helps us understand the formation of mountains, the creation of ocean basins, the occurrence of earthquakes, and even the distribution of plants and animals across the globe. But you might be wondering, how do the tectonic plates move? Well, there are three types of movements: transform, convergent, and divergent movement. Transform movement is defined as the plates sliding past each other horizontally. Easy, right? Convergent movement is defined as two plates moving towards each other. Here, we can have two situations depending on the density of the plates approaching each other. Imagine two plates with the same density. Both of them float on the same level over the hot molten inner layer of the air. What happens when both of them meet? As these plates meet, the crust buckles and folds, forming a large mountain ranges, such as the Himalayas. We rarely find volcanic activity in these formations. Now imagine two plates one denser than the other one. The denser plates dive beneath the less dense plate in a process called subduction. As the subducting plate sinks into the inside of the Earth, it begins to melt. The molten rock is less dense than the surroundings, so it rises through the crust. As it reaches the surface, a volcano or a line of volcanoes, called a volcanic arc, is formed. Do you know where you can find these examples of these volcanoes? The Cascade Range in North America, which includes Mount St. Helens, is an example of this type of volcanic activity, when the process happens on land. On the other hand, the Japanese archipelago is the result of underwater subduction. But hey, when does the divergent movement occur? Divergence occurs when plates move apart, resulting in the creation of crust. As the plates separate, the hot molten material, called magma, inside the Earth and tends to fill the gap between the two plates. Divergent movement can occur underwater, where the emergence of magma inside the Earth from underwater volcano and volcanic mountains are called Mil-Rosian ridges. Eventually, with time, the magma cools down, and new magma can flow towards the surface and deposit on top of the cold material. If enough material is deposited, the volcano might rise to the surface to form a volcanic island. Divergent boundaries can also occur within continents, forming rift valleys. As the plates separate, the magma rises to fill the gap, creating volcanic activity along the rift zone.
Volcanic eruptions emit gases, lava, and tephra into the atmosphere. The gas phases are made of water vapor, carbon dioxide, and sulfur, among others. But did those gas phases favor the origin of the atmosphere and the condition for life in our planet during the Precambrian era? Volcanoes represent the 80% of the Earth's surface above and below sea level. There are two theories that explain the origin of our planet's atmosphere. One, volcanic outgassing, which occurs in active volcanoes and describe the emissions of gases that remain dissolved in the magma. And during magma ascent and decompression, they become released from the Earth's interior to the atmosphere. For example, Int'l is a volcano that is constantly releasing carbon dioxide into the atmosphere, producing the 10% of the overall carbon dioxide concentration globally. Or two, through planetary accretion, which occurs when rocky planets smash together. Based on the first theory, volcanoes release trapped gases of hydrogen, methane, and ammonia from the Earth's primary interior to the atmosphere and played a pivotal role on the development and maintenance of the Earth's crust and its atmosphere, leading to those stable conditions that aided the development of life and saved the Earth's baseline climate. Volcanoes supplied the ingredients vital to evolve and sustain life. Until the Earth's core formed, volcanoes released emissions similar to the modern volcanic gases that we find nowadays, namely water vapor, carbon dioxide, and others. As this surface was gradually cooling, the water vapor condensed to form parts of the Earth's oceans. In submarine volcanoes, the ejection of hot fluids form hydrothermal vents, which currently host dense and diverse biological communities, such as microbes, bacteria, and archaea, which harvest chemical energy from the dissolved gases and deposited metals. It is quite possible those communities resemble the earliest microbial ecosystems on our planet.
Obviously, human-induced climate change is one of the major factors having a negative impact on the ocean side as well. One well-known consequence of global warming is, of course, sea level rise due to ice melt and thermal expansion of the ocean water itself. It will likely reach between 0.5 meter and 1 meter by the end of this century, and while this might not sound like a lot, it already means that densely populated areas in countries such as China, Vietnam, Japan, and many more are at risk of being flooded, and this would affect hundreds of millions of people. Many solutions are being discussed for protecting coastlines and the people living there, including seawalls or barriers. But to attack the problem at the source, limiting global warming is, of course, the most important solution. Another impact on the ocean under global warming is ocean circulation changes, and something that is being discussed a lot is the potential for a future weakening or even a collapse of the circulation that connects the surface and the deep ocean in the Atlantic. This is called the AMOC. And when people talk about this, they more commonly refer to the Gulf Stream, which is bringing warmer waters northward, giving Northern Europe a warmer climate than it otherwise would have. In reality, the Gulf Stream is only one part of the AMOC, and in a warmer climate with warmer polar areas, the concern is that there will be less cooling of the surface waters and more fresh water due to melting ice and precipitation. And this could prevent surface waters in the north from sinking to greater depths. And consequently, this could slow down the transport of warmer waters northward in the extension of the Gulf Stream. And modeling studies show a consistent future weakening of the AMOC, but in observations, there is not yet a clear direction of change. Our time series are still a bit too short though, so we keep monitoring how this evolves. April and May of this year have produced record highs in global ocean surface temperatures, which can be described as a global marine heat wave. Temperatures have been as much as 5 degrees Celsius above normal for this time of year in the North Atlantic, for example, around the UK. And this event stands out as unprecedented for the period that we have observations from, so since about 1850. And the North Atlantic heat wave has also started unusually early in the year. Marine heat waves have serious consequences for marine life and are known to cause things such as coral bleaching, mass death in fish populations, etc. They likely also affect land temperatures and thereby the risk of heat waves on land too. And then in tropical areas, warm surface temperatures act as a source of energy for tropical storms. And an increase in marine heat waves means that the areas with sufficiently high temperatures for tropical storms simply expand. As sea surface temperatures rise, the water also loses some of its ability to hold dissolved gases such as oxygen. And in addition, a warmer surface layer is less dense, and the increased density difference between the upper and the deep ocean tends to slow down ocean circulation. So oxygen is being supplied more slowly. And the global upper ocean seems to have lost about 2% of its oxygen between 1960 and 2010. And the volume of anoxic waters, so water with no oxygen at all, has quadrupled actually. This is very likely a consequence of human-induced changes, including global warming and nutrient pollution as well. And a decrease in oxygen levels can lead to major impacts on marine ecosystems and thereby also on fisheries, of course. Ocean oxygen is expected to continue to decline in the future, so climate mitigation and nutrient reduction strategies for sewage and agriculture are central to reducing this problem.
While oceans represent 97% of the Earth's water, the human life is made easy mainly thanks to fresh water. And among them, groundwater is the most important available resource for the humanity. However, this subsurface water from pore space and rock is being already impacted by climate change, both in terms of quantity and quality. Yet these effects are still poorly known and underexposed. The increase in variability in rainfall and extreme weather events due to climate change can cause relative long periods of drought and flood, which directly affect the availability of groundwater. If floods, for instance, can contribute to recharge the aquifer, they also facilitate contaminants infiltration. High rainfall events increase the water table, and the more the groundwater table is close to the ground, the more the groundwater vulnerability increases. Indeed, extreme precipitation by leaching diverse materials and waste on the soil surface can contribute to increase the concentration of chemical elements in groundwater. We have major ions such as fluoride, sodium nitrate, and heavy metals, which are a major concern with damage on people's health. Moreover, waterborne diseases have been often recorded in after flood events among groundwater users. And this is particularly true for regions where there is a poor sanitation systems. Now let's talk about drought. Drought leads to groundwater decline with impact on surface water, wetlands, and all groundwater dependent ecosystems. it is worldwide noting that a return of rainfall after drought event does not guarantee that the depleted aquifer will gain its previous level. Researchers found that the more droughts are severe, the more the time needed for groundwater to recover increase. And this is peculiarly true for coastal Iceland and coastal area where a decline of groundwater combined with its sea level rise can cause its seawater intrusion. In fact, decline in groundwater can have many water quality issues. As water drops in the aquifer, they also facilitate the mobilization of heavy metals or any other contaminants. So droughts start with a water quantity problem, but the end might result in water quality issue. Another point very important is that the climate change, by affecting the season, leads to a variation in groundwater recharge period. We already observe in many places an early or a late recharge of the aquifer. And this have many consequences on human activity and especially on agriculture. So it's clear that the climate crisis is a water crisis. Groundwater monitoring programs must be developed to anticipate irreversible effects and for early warning systems.
So there are evidences all around us, since climate change is happening in all places and in all times. So the most obvious would be the melting of Arctic sea ice, Antarctic ice sheet, and mountain glaciers. In the Arctic, sea ice is becoming increasingly less, decreasing by about 50% in the past 40 years. And in the Antarctic, the Larsen Sea ice shelf completely collapsed in 2017. And many mountain glaciers have also significantly shrunk or even disappeared in the past half-century. So the melting of these glaciers then resulted in a rise of global sea level. On average, sea level rise by about 3.7 millimeters per year. This greatly threatens the coastal cities and island countries. And moreover, climate change is not just warming everywhere, it's more about extremes. So in the past several decades, we've been experiencing more extreme weather than ever. We have heat waves here and cold surges there, floods in some areas and droughts in others, etc. Like in the past 2 years, North America and Europe suffered from extremely cold winters, which were actually due to the warming of the Arctic. The Arctic became so warm that it could no longer trap the cold airs within the polar area, allowing them to penetrate to the lower latitudes. And right now, in the Northern Hemisphere, especially Asia, is experiencing a hotter than normal summer. And this is likely because of both global warming and a developing El Niño event. These are all consequences of the abnormal atmospheric circulation patterns associated with the increase of greenhouse gases and aerosols. And what's even worse, these extremes are projected to become even more frequent in the future if global warming continues. Well, many aspects of the atmosphere have been affected. The thermodynamic structure has been changed because most of the warming associated with increased greenhouse gases happened in the troposphere, while the stratosphere shows some sign of cooling. It also changed the amount of water in the atmosphere. The atmosphere can now hold more water since the global average relative humidity is mostly constant. So with this more water, there will be more clouds and heavier precipitations. And also the atmospheric circulation patterns have been changed by global warming, especially due to these unevenly distributed warming patterns. And this may also change global environment by affecting the distribution of trace gases and aerosols. And these changes may further feed back to the climate and alter the global warming pattern. So it's a very complicated system that needs a lot of research. So now the most widely believed solution for a more sustainable Earth is a change of the energy structure. Because most of the warming comes from the consumption of fossil fuels, so we must find replacements. Solar, wind, and hydropower, they are all good candidates, but not very stable. Nuclear power, if safely managed, may be the solution. But the most important thing is that we must keep a peaceful world, because any wars, either hard or soft, may affect our unified goal towards a more sustainable Earth.
The cryosphere encompasses all parts of the Earth system where we find water in solid form. This includes glaciers, ice sheets, sea ice, snow, and permafrost. People generally think of the cryosphere as just the region around the poles. But in reality, we find the cryosphere far away from the North and South poles too. Glaciers are found in every mountain range, on every continent except Australia. And furthermore, we have seasonal snow cover on large parts of the Northern Hemisphere. So we all know what snow and ice is. But did you know how much each of us benefits from the cryosphere? On one hand, the cryosphere helps to regulate the Earth's climate by reflecting sunlight back into space. This helps to maintain the Earth's energy balance and prevents excessive warming. On the other hand, ice on land in form of glaciers and ice sheets play a further important role for the Earth system through its ability to store vast amounts of fresh water. Importantly, ice mass changes on land directly impact global mean sea level. Now imagine the Antarctic ice sheet. It has an area larger than Europe and a thickness of up to 4.7 kilometers. All ice. If the entire Antarctic ice sheet would melt, sea level would rise by about 58 meters. So what are the effects of climate change to the cryosphere? As climate changes, the cryosphere changes with it. Thankfully, many of its components have been observed for a very long time, and satellite networks have been continually improved and expanded to monitor the cryosphere. For example, using satellites, we have been monitoring sea ice extent for 4 decades and ice mass changes for 3 decades. That's very valuable data. That's why we know that global warming has led to a widespread shrinking of the cryosphere. The Arctic region is experiencing a rapid reduction in both sea ice extent and thickness, with far-reaching consequences for the Earth's energy balance, ecosystems, as well as indigenous communities. Climate change also affects glaciers and ice sheets, particularly in areas where ice is in direct contact with warm ocean water. Here we observe increased melting as well as an increase in ice discharge. Furthermore, these rapid changes could lead to instabilities which further accelerate with ice mass loss. Permafrost is also affected by climate change. As temperatures rise, permafrost thaws, causing the ground to become unstable. Problem is that thawing permafrost releases trapped greenhouse gases, such as methane, which further contribute to climate change. What is our role in all this? Evidence shows that the majority of cryosphere changes we observed in the past few decades are a result of human influences. This anthropogenic climate change is a result of more than a century of unsustainable human activity. Thankfully, we have the tools and the know-how to limit global warming. The next few years are critical, and organizations like the IPCC show us how taking action now can result in a more sustainable and better world in the future.
Part of society surely has an infinite wish to transform these destructive interactions of humans and Earth to a sustainable way of life, where humans and the Earth can interact harmoniously. Have you thought about which small step you can take in your house or small community? How do you want our future generations to see and learn from us? Shall we join and transform Earth-human connections together?